Next talk will be given by Professor Emanuel Tutuc from the University of Texas at Austin, and he'll go to talk about to twist or not twist adventures in Flatlands.
All right, thank you, Hongi. I want to thank the organizers for having me here. This is the best title I could come up with, and really summarizes the dilemmas that sort of my students and I have when designing experiments. And I'm going to illustrate this with a few highlights here. And a common denominator in many of this is that Allan was encouraging us and supporting and basically guiding some of this work. All right, so this is a very important slide. I want to acknowledge all the students that did the work, my collaborators here at UT and also at Arizona, as well as the funding agencies that kept us going. And since I guess I'm the first experimentalist giving a talk on 2D materials, I just wanted to flash this sort of summary of 2D materials that we're using in our exercises. Graphene, carbon atoms in a honeycomb lattice, boron nitride. These are basically same structure, but replacing one site with boron, the other one with nitrogen. Graphene is a semi-metal, very high mobility. Hexagonal boron nitride is an insulator, also has atomically flat surface. And then transition metal dichalcogenides. In this talk, transition metal dichalcogenides is going to be a supporting actor. We're going to use it as a tunnel barrier. Chemical formula MX2. Also is a semiconductor, gaps somewhere between 1 to 2 electron volts, depending on the combination of the metal and the chalcogen. One difference is that compared to graphene, it has strong spin-orbit interaction, although that's, again, like I said, is not going to play a role in this talk. All right, so this is the summary of the talk. And since the emergence of graphene and other 2D materials, basically the community has thought is basically the first thing, or one of the first things is let's make heterostructures, right? Let's make heterostructures that combine 2D materials, and those heterostructures are heterostructures that would otherwise not be available in nature, cannot be grown by thin film deposition techniques, molecular beam epitaxy, and so on. So we started to work on that too. So this is one of the earliest heterostructure, perhaps the first. This is a double layer, 2 graphene layers separated by a thin dielectric. This was aluminum oxide. By today's standards, this is a very low quality sample, but still it was enough to allow us to measure Coulomb drag in this system. And we got some early encouragement to work on this from Allan. This is an email from 2007 that I just dug up over the weekend. This basically was made to try to test some of these hypotheses that if you bring 2 layers in close proximity, electron interaction would lead to pairs of electrons and holes and maybe superfluidity. We haven't seen that in the system, but this is going to be a common denominator in other experiments that I'm going to talk about, okay? So let me take a bit of detour and talk about heterostructures. As an experimentalist, when I think about heterostructures, I'm used to draw a band diagram with barriers and wells, and we use envelope functions to basically represent the states in a quantum well. And if we look closely, basically the basis for this is that, let's say in a structure grown by molecular beam epitaxy, you have registration from one layer to another, from one layer to another. And that registration gives us for granted the fact that the in-plane electron momentum is a good quantum number from one layer to another, okay? If you work on MBE grown structure, you take that for granted, okay? But if you make heterostructure of 2D material that are stacked, perhaps without twist control, this assumption it basically no longer holds. In-plane momentum is no longer a good quantum number, okay? And this was the type of heterostructure that I could understand, because if I were to have, let's say, 2 layers that are in close proximity and we can do a tunneling measurement from one to another, if the in-plane electron momentum is a good quantum number, we can actually measure the hopping energy from one layer to another. This is done through a tunneling measurement, basically that uses energy and momentum conservation. So if you think of two band structures, if there are a line, okay, energy and momentum are conserved in tunneling, and if you misalign them in energy space, then energy and momentum conservation no longer hold simultaneously, okay? So this was the type of structures that I could understand. The experimental signatures are gate-tunable negative differential resistance. We can actually model this with a relatively simple model, okay? And there's been a lot of work done, particularly in gallium arsenide. Probably Jim is going to talk about it tomorrow. And sort of more recently on graphene as well, although some of these structures were actually approximately twist control by not actually twist control. Now, the key ingredient in this, again, is in-plane momentum to be conserved in tunneling. And for in-plane momentum to be conserved, it has to be a good quantum number. So this is a simple structure to understand in tunneling, but actually more difficult to realize experimentally. So how do we actually enforce this in-plane momentum conservation? And the way we would do it experimentally is to align the layers in real space, because aligning them in real space would align the brilliant zones in momentum space, and that would ensure the fact that the electron momentum is a good quantum number if electron momentum is conserved in tunneling. Okay. So the technique is, in hindsight, a straightforward one. We would start with the large grain of a 2D material, in this case graphene, and we would split it into 1, 2, 3 different sections, and then pick these sections sequentially, either by night twisting, or if we desire to introduce a sort of a twist, we could twist the stage. So I'm going to just illustrate this here. We've gone through different setups over the years. We started using a commercial mask aligner, and then we built one that is in the lab, and today experimentalists can actually buy this commercially. Okay, so it goes like this. We would start with the stamp, and then this is the 2D material that is split into 2 sections. Pick the first, and then pick up the second one. We could twist if we need to, but in the structures that we'll examine first, we're not going to twist, okay? So this is how we ensure twist control in a van der Waals heterostructure. So let's test this with a sample that consists of 2 bilayer graphene separated by a tunnel barrier, okay? And the choice here is done so such that this tunnel barrier, which is tungsten diselenide, has a good alignment with the sort of Dirac point of graphene. Tungsten diselenide is also a relatively high mobility transition metal like chalcogenide. So let's build this double layer that is twist control, okay? So we start with the stamp. And what you see here, those are 2 bilayer graphene that were etched out of a large flake, okay? So we're going to pick up the first one right here, then pick up the tunnel barrier, and then we'll pick up the second layer, the bottom layer, and then land this onto an HPN substrate, metal contacts to the different layers. So this is the sample. These are contacts to the top layer. These are contacts to the bottom layer. So let's do this tunneling measurement that would tell us, on one hand, if we have twist control, and then what we learn about the sample. Okay, this tunneling measurement is going to be a 4-point measurement, and it shows textbook gate-tunable negative differential resistance at room temperature. Very nice resonant tunneling, so it's good. Twist control is present here. It ensures momentum conservation in tunneling, okay? We can actually understand the different features in tunneling depending whether we tunnel from a conduction to a conduction band, to valence band, or we can also tunnel between a conduction to a valence band when these ring of states, basically when the 2 bands intersect. So we have what we call like band tunneling and unlike band tunneling. Right. We can actually model the tunneling characteristic in the sample using a relatively simple model. There are only 2 parameters in this model. There's a hopping energy from one layer to another. There is and also there is a quasi-particle state broadening. So in this sample, the hopping is 30 microelectron volts, small but finite, and gamma is 2 to 10 millielectron volt. All right. So this is good. This is a sort of a textbook sample. We're satisfied with this. Let's also test the twist control. So what we can do is we can apply an in-plane magnetic field, and an in-plane magnetic field in tunneling is equivalent to a momentum shift. That momentum shift is shown here, in-plane magnetic field. D is the distance between the layer. What an in-plane magnetic field should do, it would take a resonance and split it into two resonances. The splitting is proportional to the value of the in-plane magnetic field. And we see that very clearly here. And the only thing I'm showing this is that the magnetic field where we see the splitting is 5 Tesla. 5 Tesla corresponds to an angle of 0.4 degree twist. So in other words, the twist control in this sample is better than 0.4 degree. Okay. So good. So we have, this is interesting. Now let's put this to work. So we're going to choose two examples here. Now, one theme that's been studied in my lab and in many others were the moire materials. We looked at twisted bilayer graphene. I guess we saw some of the initial signature of correlation and flat bands. Okay, twisted double bilayer graphene. Again, this is a system that has flat bands, shows correlated insulators. We've actually complicated the sample structure where we take a moire material and we add a gate that we can probe resistively, and this can serve as a resistively detected Kelvin probe that allow us to measure the chemical potential of the electrons in the moire material. This is very useful to probe, for instance, topological properties. This is alternating twist quad layer graphene that shows correlated insulator and superconductivity. I'm not going to talk much about it. I guess Pablo is going to talk about this tomorrow. This is the discovery that really elevated the field. Okay, and Rafi is going to talk about it as well. The flat bands in moire material, they give rise to superconductivity in correlated insulators and also more recently fractional Chern insulator. What I want to come back to is the very first structure that we discussed, the double layer. Okay, and Shankar already discussed the Bose-Einstein condensation in the system. In essence, if you take either in the zero magnetic field or in magnetic field, we take Landau levels and populate them such that half filled, electron interaction would favor the pairing between, I guess, particles and holes, and they should form the superfluid that can be probed through a variety of techniques. Those will be either tunneling or drag, okay, or counterflow. All right, so this is the state that we would like to probe. Okay, it's a linear superposition of, let's say, a state in the top layer and a state in the bottom layer, and the space factor right here is what determines the coherence of these pairs that form in this system. All right, so this has been studied for also many years, and I guess Jim, who was supposed to actually talk in this session, will talk about it tomorrow. And as I said, there are two ways to interrogate the state, either tunneling or drag, okay? So what are the requirements to interrogate the state to tunneling? So if we go back to the sort of basics, the Josephson junction, okay, there is a critical current, and the critical current is proportional to a Josephson energy, which is the energy to take a Cooper pair from one superconductor to another. Now, in this system, the situation is slightly different. This critical current, there are theories that have been developed over the years, and a common denominator in all this theory was Allan and also Steve, who's in the audience. In essence, this critical current requires a finite hopping energy from one layer to another. Okay, without this finite hopping energy, there is no critical current. There is no Josephson effect in the tunneling. Okay, and this has been formalized very nicely with this pseudo-spin framework and ferromagnetism. In essence, coherence pairs. So in this language where top is the top layer, spin down, pseudo-spin down is the bottom layer, the states are really linear combination that live in this XY plane, okay? And this U1 symmetry is what ensures coherence. But if we go to the theory papers, there's a number of them. The common thread is that the critical current of the Josephson tunneling is proportional to this T square, which is the hopping energy from one layer to another. So in order to see Josephson tunneling, we need this single particle hopping energy from one layer to another. And in order to have that, we need twist control, all right? So let's test this hypothesis. So what we're gonna do, we're gonna take a double layer where we have independent contacts to both layers, but we also have twist control. These two layers are twist aligned, okay? And this is a sample. This adds complication because not only we have to make a double layer, independent contacts, sample quality has to be good, but also twist control has to be used here. If we do the tunneling measurement from one layer to another, we see here a prominent feature. This is the resonant tunneling when the energy bands are aligned. That would be if you want this picture right here or this picture right here. So this is a small interlayer bias. This is a large interlayer bias. This dashed line are the Fermi levels of the two layers. So this is an example of the actual data. We can actually fit this and back out an interlayer coupling, which is small but finite, 1 microelectron volt, okay? So let's now take the sample, put it in the high magnetic field and do a tunneling measurement over there. Okay, what we see is that this resonant tunneling now basically breaks into the squares, and those are in essence the Landau level in the two layers. So this would be 1, 1, 2, 2, 3, 3, 4, 4. And when I label this is basically is the orbital Landau level index because there's also a fourfold degeneracy due to spin and valley. Okay, so the single particle tunneling with momentum conservation is reflected also here. Okay, so now let's focus on the n equal to 0 sector. This is when the two layers are in the n equal to 0. If we look closely there is a pattern that emerges where we have resonances when the different Landau levels are half filled. Okay, so this is what is expected theoretically. Okay, and the fact that we see this is precisely because we have this single particle hopping energy from one layer to another. Okay, but this is not necessarily evidence of coherence. You can get tunneling if you simply have high density of states. So if, let's say, interaction splits the fourfold degeneracy Landau level, you could get these peaks simply from a high density of states. So let's dig a little bit deeper into these peaks, okay? And what we'll do, we're gonna park our gates at a certain filling factor, and we're gonna do an IV tunneling measurement. And what we see in all cases, we see a very sharp resonance at 0 interlayer bias, and it stays at 0 interlayer bias irrespective whether we tune the filling factor or the density in the two layers. So the evidence for coherence here is the fact that we see a 0 bias tunneling peak that is immune to variation in the layer densities, okay, to a certain extent. So this is filling factor changing them in the same direction or in opposite direction. And the signature is only present in the n equal to 0 sector. If we go outside, we don't see this. So in essence, what we see here is the message that I want to give is that if you want to see Josephson tunneling due to this pairing, single particle tunneling is necessary. And for single particle tunneling to be present, twist control is necessary. So how strict is the requirement? So this is a 0 degree device. This is a 1.3 degree twist between the layers. You see here that the tunneling in the n equal to 0 sector is gone. Okay, so why is it gone? Well, we can take these cones. Those are the band structure in the two layers. We have Landau levels. We displace them in momentum space. So certainly the n equal to 0 tunneling is the one that is most sensitive to twist. Okay, so that's why the signature is gone right here. You could get tunneling in the higher Landau levels, but not in the n equal to 0 sector. So this is very nice. In essence, in order to see interlayer coherence through tunneling, single particle hopping is needed. And in order to have that, twist control is needed. And we can understand the different states that we see if we invoke spin and valley splitting in the n equal to 0. And in essence, we see them only when we tunnel between states with the same spin orientation. So spin conservation also plays a role when we test the signature of coherence through tunneling. All right, so I'm getting close to the end of the talk. Moire materials are interesting, double layers are interesting. What's more interesting? The double moire. So this is a system that consists of two twisted bilayer graphene that where the top two and the bottom two layers are twisted by a small angle, and the third and the second layer are twisted by a large angle. And what this leads, if we look at the resistance as a function of top and bottom gates, we see this pattern right here, okay? What this represents, it's evidence that we have flat bands in the top twisted bilayer graphene and the bottom twisted bilayer graphene. Those regions of high resistance are the gaps when we filled those Brillouin zone in the top twisted bilayer graphene and the bottom twisted bilayer graphene. So we can basically take this data and map it right here. So this is when we fill the top and the bottom. This is on the valence side. This is keeping one at charge neutrality. This is keeping the other at charge neutrality. An interesting observation can be made by looking at this data is that if we were to track the charge neutrality at 1 TBG, this profile right here represents the chemical potential of the other TBG. So this system, in essence, gives us the chemical potential as a function of density of the two TBGs simply by tracking the charge neutrality of one or the other, okay? So if we track, for instance, the charge neutrality of the top TBG, that is the chemical potential as a function of density of the bottom TBG. So interesting observations. I guess we're sort of at the start of exploring the system, and I think other groups are doing too. But I guess I'm going to conclude with the summary here. And I guess I wanted to thank you all, in particular Allan, for inspiration across the years, and be happy to take your questions.
Hi, thank you for your talk. Can you also do this Josephson tunneling experiments on TMDs?
We have done tunneling measurements on double layers of TMDs to probe for, let's say, single particle tunneling, but we have not looked for the Josephson tunneling in the states where, I guess, not in high magnetic fields. Okay, so we have done what I would call resonant tunneling in double tungsten diselenide layers separated by a tunnel barrier.
Okay, thank you.
There are some difficulties in making contacts to both the conduction and the valence band in a TMD in order to explore the tunneling in the manner that I described in the graphene system.
I wanted to ask if you can test Shankar's theory.
So I guess you'll have to explain. I think you went too fast for me. What was his theory?
T is equal to 0. There is no phase transition, period. At T is equal to 0,
yeah,
we have either a BCS.
Yeah.
There's a TC, which could be very sharp. There's a finite temperature. But at T is equal to 0,
yeah,
there is just one phase.
You know, so I don't think realistically. Yeah.
It's a sharp also.
Yeah. So I mean, no, I think that if you're the strict experimentally, one cannot access the T equal to 0 regime. What I will say, okay, what I will say is that in a system, in the double monolayer graphene system, this zero bias tunneling peak that we attribute to interlayer coherence, and I think that I don't think that's controversial at all, persists up to relatively high temperatures. Certainly 40 Kelvin, we see, yeah.
The point is not high temperature. The point is low temperature. The question is very simple. suppose you could do an experiment at T is equal to 0.
Uh-huh.
Would you see any phase other than just the coherent? People normally think, oh, we make the set layers very well separated, they'll be correlated electron hole. Okay. The theory says no, there isn't. TC will go down exponentially.
Yes.
So you cannot access it. So you could look like an independent electron hole.
Yeah.
Because TC is very low. So question I'm addressing the pre-observable question.
Okay.
Which I don't understand. Cannot be for some clever way. But any phase transition is only a finite temporal MacDonald phase transition. There is no quantum phase transition.
Yeah.
I guess the answer is no.
No. I didn't want to say that.
Yeah, thank you. And I think I have another question. So do you think this Josephson tunneling experiment can help to distinguish between different mechanisms of pairing or even different types like BCS, BEC, etc.?
Okay, so I'm going to take I'll provide a simple answer to this. Okay, what we can do, I'm not sure. I think that going into advocating for a certain model or another it can be dangerous sometimes. What I will say is that tunneling is a more sort of powerful technique compared to, for instance, to drag, because tunneling can give access to the coherence length, which drag cannot probe directly. Okay, so by doing in-plane magneto-tunneling of the Josephson tunneling yields the coherence length, and it could also yield the temperature dependence of the coherence length. Okay, now, so for instance, if we see where a transition, let's say the coherence length is short in one regime and long in the other, I could probably associate that with the BEC or the BCS regime. Okay, but that is more of a question for theorists. What we would say is that experimentally we would be able to probe the coherence length as a function of different parameter in the system.
Okay, thank you.
Yeah.
Any other question?
Sure. So I'm not sure what I'm asking. So you decide, right? So can you distinguish between a really superfluid phase with interlayer coherence and some sort of electron hole droplet like they discussed, where there is a very large, it's a macroscopic bound state essentially of electrons and holes, and there is a very large polarizability of that droplet when you try to push it, from layer to layer. But there is really no coherence in the sense of, expectation value of psi dagger up, psi, up layer, psi down layer, that type of stuff. Can these be distinguished at all in any kind of experiment or not?
So I guess if this electron hole, what do you say, plasma or bubble?
Electron hole droplet, I think.
Okay.
Right.
I would need to understand whether the tunneling, this enhanced tunneling is sensitive at all to the densities in the two layers. Okay, because and I didn't, I could go on to sort of a deeper discussion of the tunneling signatures. What we see in the double layers in the quantum Hall regime at half filling factor is that the zero bias tunneling peak, let's say the Josephson-like tunneling, is immune to variations in the layer densities. It stays entirely at zero. Okay, at zero bias.
What you showed, maybe I missed this part, was proportional to T squared in the end, right? So, which is not quite Josephson tunneling, right? There is some either strong, phase breaking or something like that.
No, there is entirely consistent with Josephson tunneling. The critical current in a Josephson junction requires the single particle hopping from one layer to another.
Right, but one thing is being, current being proportional to T, and another thing is being proportional to T squared, which is sort of a rate at that point, right?
Yeah, I think, yeah, it's proportional to t squared. That is, I guess we can go, yeah,
Okay.
Okay.
No, no. Right. Thank you.
Yeah.
Okay, any other question? So, well,
Thank you so much
Yeah.
for the wonderful talk. So, measuring this tunneling current and getting the coherence information is quite exciting. But have you thought about having a momentum distribution by some kind of angle-dependent measurement and try to have the convergence of the momentum at the ground state and then experimentally try to see how that correlate with your tunneling current? That would be wonderful, I believe.
We have not considered that.
So when you have a momentum distribution and you have a coherence, all the particles are like a come to the ground state, right?
Right.
And then you are getting this coherence length or distribution from your tunneling current, right? So people try to see this BEC state also coming to the ground state in the momentum distribution by doing some angle dependent measurement like RPS or angle dependent photoluminescence. And then I'm curious to know if you thought about correlating your direct tunneling current observation to that kind of momentum distribution curve.
Yeah, I think I know. Yeah, I think I know what you're referring to, but I think the situation is different. And I think you may be referring to a bona fide Bose-Einstein condensate, right? When all the bosons, they go into K equal to 0 state. Okay, that's not what's happening here. So here the coherence is between the states, let's say in the top layer and the bottom layer with the same momentum. Okay, and there would be a phase factor when we construct the superposition, and that phase factor will be the same for all K values. Okay, but the electrons would occupy all the K values in a lambda level.
Thank you.
okay, if there's no more question, then let's thank the speaker again. Okay.